There we are. We should be live. Excellent. As people are filing in to the live stream that we've started, I just need to make sure that my audio levels are where they need to be. So please let me know if it's too... I'm trying to check the audio levels right now, but if I'm too loud or if I'm too soft or something along those lines. Just give me a thumbs up saying, hey, I can hear you and I can see you, and you're doing a live stream. I'm like, hey, that's awesome. Yes, I am doing a live stream. As people are, again, jumping in and filing in according to the link that I sent y'all, which is great. It's going to be great. I'm so excited. Oh, goodness. Here we are again, stuck at home. Here we go. She says I'm good, so we're good. But yeah, here we are, stuck at home. I don't know. It's one of those things. Oh, the front door opened. Sorry, I'm home right now, obviously, but my wife was taking my daughter out to the store. Well, not really to the store. She wouldn't take her into the store. It was more of a like curbside pickup thing. But they probably just stopped home or something like that. But anyway, while you guys are filing in, let me just give you a few reminders and tell you what you are in store for today. Oh, there's my wife. Hey.
He wants to come.
Oh, the stuffed animal. Oh, that's the real cat. Nothing. Goodness gracious. Anyway, so what we're in store for today, as the title of the video suffices, she's selling your daughter. No, she's not. At least I hope she isn't. But anyway, as the title indicates, we're going to be going over certain polynomial attributes that I would like you guys to put into your notebooks, of course. But we'll get there in a few minutes. Afterwards, I would like to review certain problems with you in preparation for the assessment that I have set forth for you. As you probably saw yesterday on Google Classroom, there was an assignment for an assessment through Edulastic that I wanted you guys to complete. Now, typically, if I was going to give you an assessment in class, which was my hope, was to give you an assessment in class today, this Tuesday, but obviously Sunday changed everything. So here we are online. So in order to reconcile those two things, I decided, okay, I'm going to give the Edulastic assessment online, and I'm going to make the due date tomorrow at 2 o'clock, and that'll be sufficient. But yes, I need that assessment done. I need that assessment done. So please make sure that you're working on that after we are done with said class. Now, technically, I have you from 9:24 to 10:24. I am not going to keep you for the entire time. And of course, if you do have any questions, of course, you can throw those questions directly into the chat. That would be awesome and sufficient, simply because I want to be able to answer your questions live. But of course, there are certain things that I would like to go over with you first. I have an amazing setup here, which I really enjoy. The setup that I have, I can do a website shot right here. Like, that's the screen that I'm kind of looking at right now. With, you can see like the chat on the side. I can see how many viewers there are and things of that nature. It's a really nice little setup where I can do a wide shot, and there I am right there, and I can transition between these things. It's really awesome. I could do I'm back in 5 minutes thing, and I can turn off the audio for that. But no, this is my top-down perspective. My top-down perspective, you can see that I can write things just like I do in the classroom, but the benefit is there is no glare. There's no real glare for those who are online. It's really fantastic. But that's really what I have in terms of an online setup at home. That's how I'm able to stream pretty nicely. I really enjoy it. I like it. I like it. So, as I said, and again, I'm stalling just to allow more people to kind of get into the chat, because if people are not here, they are going to have to watch it later, and it's up to them, and they're going to be like, Mr. Markey, I don't remember learning that, and I'm going to be like, you were not there for the live stream, as I told you you should be. But anyway, ladies and gentlemen, if you would, I'm going to need those notebooks out and open. Yeah. Today is the 24th. And I am entitling this Polynomial Practice and Attributes. The attributes I'm going to do first. I probably should have called it attributes and practice, but I'm going to do the attributes first, and then I'm going to do the practice afterwards. And that practice, of course, is in preparation for what you guys are going to be doing on that assessment, but we'll get there when we get there. So, first things first. Let's talk about the degree of a polynomial. So I'm going to give you a few examples right here, a few examples of just random equations. Y equals x squared plus x minus 1. It's a quadratic. We'll deal with it in a moment. Y equals 3x to the 4th minus x squared. Again, quartic is what they call it typically, which is nice. So, yeah. A linear equation. Let's just keep it simple. Y equals 2x. I don't know. And just for the fun of it, let's throw in a cubic equation. A cubic equation of y equals x plus x squared minus x cubed. Now, just for the sake of argument, I'm going to create a little chart here around my things. Talk about the degree of a polynomial, and then I'm going to give you the definition as to what it means to be the degree of a polynomial. Now, the degree of a polynomial is the largest exponent. That's basically what it comes down to. A polynomial in general, and I gave you the definition of a polynomial weeks ago, where in a polynomial, every exponent is a positive whole number. And mind you, exponent. Every exponent is a positive whole number. Doesn't have to be, like, oh, there's a negative. Yeah, it doesn't matter because it's not an exponent. Or I could have a fraction here. I could have like 1/2 x. Perfectly fine. But as long as every exponent's positive whole, you have a polynomial, and the largest exponent is the degree. Thus you have, well, x squared is the largest one, so 2 is the degree of the polynomial. It's a second degree polynomial. This one is a 4th degree polynomial. Linear equations, well, you can't see it, but boop, it's a 1st degree polynomial. Now, even though this one is out of order, it does not matter. It is a 3rd degree polynomial because the largest exponent is the one you're looking for. The definition that I can give you is the degree of a polynomial is the largest exponent. It's the largest exponent. Knowing the degree of a polynomial is going to inform the attributes that I mentioned earlier. A lot of the attributes of polynomials really does boil down to what is the degree of said polynomial, and we'll get into those details. So, let me grab another piece of paper up here, because as always, I have like blank sheets of paper to do this with. Come on, paper, be my friend. Let me flip this over. Put that over there. Again, I told you I have a nice little setup here. There we go. With multi-cameras going. I love it so much. Okay. So, let us call the degree of the polynomial that we're referring to, let's call it n. N is just the variable that I'm going to use to describe the degree of the polynomial. So if I say, the n is equal to mer, whatever it may end up being, that is the degree of the polynomial. That's what I'm referencing. So, a couple of definitions here. If we're going to let the degree be called n, then a polynomial will have at most n real solutions. if we're calling the degree of the polynomial n, then I'm going to say that any polynomial will have at most n real solutions. That is a fact. I can go back to, and I can show this right here on my calculator. Get rid of that. There we go. I can go back to some of these examples that I did on the first page. I'm just going to kind of throw these in there. X squared plus x minus 1. That was the first example that we kind of did. And if I graph that, you can see this polynomial crossing the x-axis in two different locations. It's x squared. It's a second degree polynomial. Thus, it will have at most, two real solutions, which it does. I could change this to like a plus 2. It's still a second degree polynomial. But when I graph it this time, it has no real solutions. It still fits that definition. The degree is 2. Thus, it should have at most two real solutions, meaning 2 or less. It fits that definition. I could have something like this, 3x to the 4th minus x squared. That's the second example I wrote down today. If I graph that, ooh, what's going on there? Let me zoom in a bit. Let's see what's going on there. Oh, goodness gracious. Let's zoom in again. That's nuts. In reality, this one in particular actually has 3 real solutions. 3. It is a 4th degree polynomial, so by definition, it should have at most 4 real solutions. But this one only actually ends up having 3, which still fits that definition. Everything's good there. So, next. This definition does have an alternate way of stating it. If you include complex solutions and repeated solutions, then a polynomial will have exactly n solutions. I'm going to go into more details of this in a moment. When I'm referring to, and I'm going to point my pen towards it, when I'm referring to real solutions, I'm referring to how many times it actually physically touches the x-axis. How many actual x-intercepts will this graph have? If the degree is n, then it will have at most n real solutions, meaning or less. But if you are allowed to include complex solutions and repeated solutions, then the degree of the polynomial shows you exactly how many solutions you should end up having. Let me show you a few visual examples here. Okay, I'm going to flip this screen over for myself. There we go. Good, 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 good. So, if I were to throw in, I don't know, well, let me throw in that other example, x squared plus x plus 2. I did that one earlier, and I wanted to show it to you again. Clearly, there's no real solutions. But if you include complex and repeated, then it will have it will have 2 solutions, just solutions. In reality, this one will actually have 2 complex solutions. 2 solutions where you have an I floating around in there. If I were to throw in x to the 3rd power minus 8 or some junk like that, I don't know, and I graphed that sucker, clearly, visibly, you can only see 1 real solution. But this thing actually does end up having 3 total solutions, 1 of them being real and 2 of them being complex. I'll show you another example which we're going to do the math for. We actually are going to do the math for this one in a moment. But x squared plus 8x plus 16. Now, according to the degree of the polynomial, it's a second degree polynomial, meaning it should have at most two real solutions. But if you include complex and repeated, it will have exactly two solutions. Now, if you graph this thing, look what happens to it. I'm going to zoom in. I'm going to zoom in over, come on you. I'm going to zoom in over here. Where are you? Silly graph. Go back to normal. Okay, let's zoom in. Where are you? There you are. Boom, you're going to zoom in right there. Now, what does the graph look like it's doing? The graph looks like it's coming down to the x-axis, just hitting it at a single point, and then turning the other direction, which I'm going to get into more details of that in a little bit. It looks like, and it does, only have one real solution. But, according to this definition, if you include complex and repeated, it should have exactly two. What's going on is this. The example that we have is x squared plus 8x plus 16 equal to 0. And if you were to factor that, using the factoring skills that we've been able to do, it factors into x plus 4, which produces two solutions. It fits that definition. If you include complex and repeated solutions, it will have exactly two solutions, and it does. But it will have at most n real solutions, meaning actual places that it crosses the x-axis. It's an amazing definition. Love definitions like that. Make me happy. Make me smile. Now, a couple more attributes that I want to talk about. Let's talk about turning points. A turning point. Turn that a little bit. That's funny. A turning point is when a graph changes vertical direction. A turning point is when a graph changes its vertical direction. Now, vertical direction, I'm going to show you this on a few different examples, of course, in a moment. But it has to be a change in vertical direction, meaning down to up or up to down. Let me show you a visual right here before I go to the graph for a few different ones. I'm just sketching this really roughly. Here's a rough sketch right here. This graph, this example, has two turning points. It has two turning points. It has a turning point about right here because the graph is going up, 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 and then it's, well, stops going up and begins going down, 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 down. Down here, same thing. It's going down, 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 and then after this point, it's going up, 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 up. Those are two turning points on that particular graph. Now, there is a certain definition that I want to give you in a moment. But let's just look at this one right here. This graph has one turning point, just one. It's quadratic. The turning point actually occurs directly on the vertex itself. Show you a different one. Let's see, x to the 4th minus 3x squared plus x squared plus 1. I'm just making that up. Let's just see what happens. Oh, yes. Zoom in. Look at this one. Amazing. This graph has 3 turning points. It has 3 turning points. It has a turning point right there, where it goes down to up. It has a turning point right in the middle, where it goes up to down, and it has a turning point right here, where it goes down to up. Every graph, by definition, has a certain number of turning points. Let me give you the definition. Let me give you the actual definition, and then I'll show you a couple more examples kind of going back to that. But again, we're assuming that the degree of the polynomial is still n, of course. By definition, a polynomial has at most n minus 1 turning points. It has at most n minus 1 turning points. Which is what this thing does. It's amazing. Now, for example, I can look at this graph. This is the graph that we just did. This is you can see in the corner right there, that is a 4th degree polynomial. It is x to the 4th power. The degree is 4. By this definition that we just wrote down, it would have at most 3 turning points. And it does. It actually has 3. It doesn't have to have 3. It could have less, according to this definition, at most. But at most, it would have 3. I could throw back in this example, x squared plus x, plus 8x. Yeah, plus 8x plus 16. We've done that example a couple times now. It has 1 turning point. It is a 2nd degree polynomial. It has a degree of 2, but it only has 1 official turning point right at the vertex. You could go, look at 2x plus 3. There's a linear equation. A linear equation is a 1st degree polynomial. Its degree is 1, and according to this definition, it would have at most 0 turning points. Well, think about a line. At what point does a line change its vertical direction? It doesn't. It's either always going up or always going down. It's just what it does. No turning points. One more. 3rd degree polynomial. Now, this is a 3rd degree polynomial, which means at most, it would have 2 turning points, according to this definition. But when I graph it, look what just happened. Look what just happened. I'm going to zoom in down here for a second. Hold on. I'm going to zoom in down here. Look what just happened here. Look very closely. This is a 3rd degree polynomial. At most, it would have 2 turning points. In reality, this graph has no turning points. It has none. It still fits that definition of having at most 2 turning points. But look what it does. It's going up, 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 up. And a lot of people would accidentally say, well, look, there's a turning point right there. No, it's not. Because at what point does the graph start going downward? It's not. It's still going up, 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 up. Kind of flattens a little bit, but it never comes back down. It never does. It just keeps going up. This graph that you're looking at has 0 turning points. By definition, it would have at most 2. Fits the definition. It's phenomenal. I love it so much. I love it so much. It's one of those weird things. Those are some of the attributes that I wanted to discuss with you. The ideas of turning points and degrees and how many zeros this thing would actually end up having. It is phenomenal. But right now, I want to clarify something. In regards to division of polynomials and the synthetic bar that we have been using. So, let's take a look at an example. I want to look at an example of something that you did back in the day called long division. Now, long division, you may not have done long division since maybe 4th or 5th grade. I don't know how things work in terms of when you learn these things, and I don't care because I know you learned it. And I want to remind you of a couple things. So I could take something like, I don't know, I want to get a good example here. Let's do 31. Yeah, I'll do 31. 31 divided by 2. 31 divided by 2. Now, clearly, 31 does not divide 2 perfectly. Clearly, that doesn't happen. But I can do long division here. And there's the thing that I'm getting to. You'll see what I'm getting to with synthetic in a little bit. And you do, okay, 2 goes into 3 one time. 1 times 2 is 2. Subtract them. You bring down that 1. 2 goes into 11 5 times. You get a 10. And you subtract them, and you get a 1. You get a remainder of 1. Now, there's a couple different things you can do here. With the remainder of 1, you could go, okay, R1, and be done with it. I don't want to do that. You could add an additional decimal point and continue the division, getting the decimal. And when you do, it'd be like, okay, 0.0, and you bring the 0 down. It's like, oh, 15.5. It should be 15.5, and it is 15.5, but I don't want that either. Instead, I kind of want to write it like a mixed number. In reality, the answer I want is this, 15, and it's a remainder of 1 over 2. Where'd that 2 come from? That 2 came from right here. The 2 was what you were dividing by. Let me show you a similar example. Let's do 28. Yeah, 28 divided by 3. Now, 28 does not divide by 3. You have a remainder. But let's see what we can do with that remainder. Now, 23 goes into 27. 9 times 3 is 27, but you get that remainder of 1. What do you do with it? You could continue with the long division and get the decimals, but I don't want to do that. You could do remainder 1, but I don't want to do that either. Instead, the answer that I want is I'm going to say, well, it's 9 and 1 remainder over 3. That's how I'm going to write that answer. There's going to be a cat crossing in the background in a moment, I think. Did he cross? I think he did. I could have sworn I saw him. Anyway, I don't care. He's a cat, so he probably hid. Anyway, whatever. But that's the way I want to write the answer. Now, how does that relate to what we have been doing? We have been dividing polynomials using synthetic division, using a synthetic bar. And typically, we want, just like on that homework on page 355 that you needed to get done for me, just like on that homework, you wanted to get a remainder of 0. You want a remainder of 0. Yeah, I do too. But sometimes you're not going to get that remainder of 0. Sometimes you're not going to get that remainder of 0. So what I have instead is this example. Now this example will not get a remainder of 0. By design, I'm purposefully doing that. But what do you do with the remainder? Let's see what happens. First, I'm going to create my little synthetic bar. It's a 1x squared and a 1x. So I'm going to do 1, 1, and -6 there. I'm dividing by x plus 1. X plus 1 is the supposed factor. But x plus 1 is not what actually should be happening there. So in reality, I got to put a -1 there. -1 is the potential 0. You're asking me how my day is going? My day is going great. I'm teaching. I'm teaching. Write this down. Anyway. We've been doing synthetic for a while. 1 plus nothing is 1. Multiply, add, multiply, add. And as we've typically done, this number right here represents your remainder. It represents your remainder. And the question becomes, well, how do we represent that remainder? I can't just do like r -6. Instead, I'm going to do this. This number is always going to be your remainder. Constant x. Since that is my case right here, my constant is 0, so the constant is just not going to be there. And that's a 1x. Okay. It's going to be a 1x plus, well, I don't have to do the constant, but it's my remainder divided by this x plus 1. That's how I'm going to write the answer. Just like I did with long division before. When I get a remainder, you're going to add on the remainder divided by what it was that you were dividing by. In this case, I'm dividing by an x plus 1. Let me show you an additional example to this one. An example that's very similar. It's going to get you different numbers, of course. But it's the same concept. You're not going to get a remainder of 0. After this example, I am going to get back into some of the practice problems that we should be focusing on for this edge elastic assessment that you guys are doing for me. But we'll do one more example here with division, because this is going to help solidify a lot of the things that we've been doing and to practice where certain numbers should go. Now, this one will not work out nicely. It will not. But I want to show you what that result is actually doing. I'm going to create a synthetic bar. It's a 1x cubed. It's a -2x squared. Please note for yourself the fact that there is an x term that is missing. The x term is not there. It goes cubed, squared. It's not there. You have to account for it with a 0. A lot of people ended up forgetting that, but you have to account for that with a 0. And then the 1 for the constant. I'm dividing by an x minus 4, and again, this is something that a lot of people ended up messing up a little bit on the homework, which I'm trying to correct with you by leaving the comments and talking to you about it now. But if you're dividing by x minus 4, it's really a positive 4 that you have to put on the outside of that synthetic bar. 1 plus nothing is 1. Multiply. Add. Multiply. Add. Multiply. Add. Clearly, it did not get you the 0 that you were hoping for. But what is the result that you have of this division? This number is still your remainder. That is not changing. That's your remainder from the division. It's what you have left over. So, if this is your remainder, this is still your constant, this is still your x, this is still your x squared. So this is a 1x squared plus 2x plus 8 plus your remainder over x minus 4, which is what we were dividing by. That's what this problem is doing. That's what this problem is doing. Now, to kind of parlay this into what you need to do for that, or what you need to remember for that edge elastic assessment, with this edge elastic assessment, I might do this exact same problem, but in a slightly different way. Let me show you what I mean. So Maybe, for example, I have this problem one more time, but I give you a completely different set of directions, where I say, f of x equals x cubed minus 2x squared plus 1, and I ask you to evaluate f of 4. Seemingly, this is the exact same problem. It is the exact same problem, except I am asking you to do something different. In the problem up top, I was asking for you to divide those two polynomials, and they did not divide evenly. They did not divide nicely. Instead, you got a remainder. Well, how do I express that answer? I express that answer in this way. The same exact way we've been doing. There's an equation that you can get from these numbers, and the remainder you just simply have to tack on to the end in a proper fashion. But now, brand new problem. Wait a minute, it's the same problem. It's just asking me to do something slightly different. It's asking for me to evaluate at the value of 4. Well, how do I do that? Okay, I'm plugging a 4 in. 1, -2, 0, and 1. Don't forget the placeholder for the x. The x is missing. You have to account for it. You're going to do the exact same synthetic bar that you have been doing. The input is 4. The output is 33. It's the same concept. It's just asking you to do something different. This number still represents your remainder. It still represents your remainder. The problem is it wasn't asking for you just to divide those two things. It was asking for you to evaluate at f of 4, meaning plug 4 into that equation. What do you get back? Oh, I get back 33. 4, 33. That's an ordered pair on your graph. That's what these things do. Now, this proves a lot of different things. And this is part of the review that I wanted to do with you guys today. This proves, by getting this 33, it proves that 4 is not a 0 of this particular graph, or this equation. And it also proves that x minus 4 is not a factor. It proves all of those things. There's so many different things that I can get out of the same exact problem depending on what the directions are asking. And even though the directions are asking something slightly different, I still may end up having you do the same thing. That's what you need to be aware of. That's what you need to be aware of with these particular problems. So, a couple of examples that I want to do. I just want to do 2 more examples that I have, and then if you do have any remaining questions, of course, we can talk about those in preparation for this assessment on Edge Elastic that you're doing. So here's an example problem, a completely different problem than what we've seen today. And here are my directions. Find all real solutions. Find all real solutions of 4, no, get rid of that 4, of x to the 4th minus 6x squared equals 27. Here's the problem that's in front of us. And they say, find all real solutions. Well, what must I do with this? Well, first, you do have to make sure that it's equal to 0. You do have to make sure that this thing is equal to 0. Otherwise, you cannot begin this process, just like quadratics. Just like we did with quadratics. Just like you're doing with any of these problems. You have to make sure it's equal to 0 before you continue. Okay, I'm going to find all real solutions. I got to break this thing down. It's a 4th degree polynomial, meaning, according to the definitions from earlier, it could have at most 4 real solutions. Could have. It's only asking for real solutions. It might have less than 4 real solutions. I mean, if you include repeated and complex, it would have 4, but I'm not asking for that. I'm asking for just the real solutions. What do I do first, Mr. Markey? I don't know. How about you look at the graph? How about you look at the graph? The way that we always do. If I were to look at the graph of this problem, again, equal to 0, so I put in that 27 as a minus 27. If I graph that thing out, oh, that looks terrible. The line just looked like it came down and then went back up. But that doesn't matter. Notice that it looks like it's only crossed the x-axis twice. We can work with that. It might have 4 total, but we can work with this, especially since I can visually identify what these numbers are. It looks like it's positive 3, and it looks like it's negative 3. And we're going to deal with both of them. Maybe there's more, but let's just see what happens. Positive 3 and negative 3 seem like a good place to start, so I have to prove that. I have to prove that. Well, how am I going to prove that? Oh, synthetic division. Okay, we'll start with the 3. I mean, it doesn't matter which one you start with. I'm just going to start with the 3. 3 on the outside. I'm trying to prove that 3 is a 0 of the function. I'm trying to prove that 3 is a real solution. Well, how do I do that? Okay. So 1x to the 4th. You have to put a 0 in for the x cubed. Negative 6 for the x squared. A 0 for your x. And a negative 27 for the constant. If we're correct, we should get a 0 as the remainder. All right. 1, 3, 3, 9, 3, 9, 9, 27, 0. Yep. You don't have to do it that fast. I just felt like doing it that fast. But it worked. Fantastic. Wonderful. Now, for the sake of argument, you got a remainder of 0. Constant x squared. Right, that's my cat. X cubed. That's just really funny. I don't know if you can see him. Doesn't matter. I don't care. But this is an x cubed. I took an x to the 4th, I divided out a 0, and it resulted in an equation with an x cubed. Okay, I can deal with that. Now, instead of actually writing out the x cubed equation, instead, why don't I just do another synthetic division with the other 0 that I think worked? Because I'm trying to whittle this thing down. It's a 4th degree polynomial. I divide out a 0, it becomes a 3rd degree polynomial. If I divide out another 0, it should become a 2nd degree polynomial. Let's try it with the negative 3. This should work, based on the graph. Where did these numbers come from? The graph. 3 and negative 3 came from the graph. 1, negative 3, 0, 0, 3, negative 9, 0. It worked. It worked. So hold on. Getting a remainder of 0 here and here proves that these two are indeed zeros or real solutions of the function. Okay. Did I find all of them? Did I find all of them? Well, let's look at this resulting equation. This resulting equation, remainder constant x squared, this is an x squared plus 3. Now, if you looked at the graph of an x squared plus 3, it never crosses the x-axis, which means to me, this one has no remaining real solutions. It may have complex solutions, but the x squared plus 3 has no remaining real solutions. Which means the answer to this problem are the two zeros that we found earlier, the 3 and the negative 3. It says to find all real solutions. Well, we just proved it. We proved that those two work. It's a fourth degree polynomial, so it could have up to 4, but the resulting equation has no other real solutions. Mind you, real, it does have complex, but that's a story for another day. Let's do one more example. I have one more example that I would like to do with you. Come on, little paper. Be my friend before we wrap up for today. And I'm going to remind you of a definition that we've written down in the past. Last example today. Factor completely the following equation. F of x equals x cubed minus 2x squared minus 11x plus 12. I'm asking for you to factor it completely. Oh my gosh, different directions, Mr. Markey? Completely different directions? Yeah, but it's the same process. It's the same process. It's just that you have to correctly interpret what type of solution I am looking for. Well, how do I even start this, Mr. Markey? You start this problem by looking at the graph. Look at the graph. Look at the graph. That's how I usually suggest you start all of these problems. Look at the graph. You all have graphing calculators on your Chromebooks. So look at the graph. If I were to graph this thing, ooh, oh my goodness gracious. This thing looks like it goes like up beyond the top of the calculator, down below. Ugh, that's not the point. Where does it cross the x-axis? It looks like it crosses the x-axis at -3, +1, and +4. Now that doesn't answer the question. I still have to prove. I still have to prove it. If the question's asking me to do so, I need to show the work to show that it does indeed work. Again, I'm visually looking at this. I might be wrong. I have to prove it algebraically. So, it doesn't matter which one we start with. It doesn't matter which one we start with, but let's just start with, I don't know, let's start with the 1. Let's start with the 1. It doesn't matter, but let's start with the 1. 1. 1, 1, -1, -1, -12, -12, 0. It worked. It worked. 1 is a 0 of the function. Now, 1 is not the factor. In fact, let me just give a little side note over here. This is a definition that I gave you a while ago. Now, I'll write that again. If f of k is equal to 0, which we proved that f of 1 is equal to 0. But if f of k is equal to 0, then x minus k is a factor. That is a definition I gave you a while back. A while back. That is an important definition, because it shows that since 1 is a 0 of the function, x minus 1 should be a factor. And this thing is telling you to factor completely. Now, at this point, you have options. You have options because you have taken a third-degree polynomial, you have divided out a factor, and you are left with a quadratic. Now that you're left with a quadratic, you have the option to either continue with synthetic, factor the quadratic using whatever method you want. I would use the Tucker method myself, or do the quad formula. But keep in mind, the quad formula only gets you the solutions, which actually you could backtrack into a factor. You could factor it using the Tucker method if it were indeed factorable, which, even if it's not, it still helps you. Or we do have two other zeros from the graph to see if it works in synthetic division. I'm going to try synthetic. You don't need to use the 0, that's the remainder. I'm going to try the -3. Doesn't matter which one you use, I'm just going to use it. Look, indeed it works. It indeed works. -3 worked as a 0. And by this definition, x minus -3 is a factor, meaning x plus 3, yes, but that's besides the point. So, this shows that x plus 1 is a factor. This shows, I'm sorry, x plus 1. What am I even thinking? X minus 1. Thinking way ahead. X plus 3 is a factor. Look what you have down here. Look what you have down here. Remainder, constant, x. That is resulting in an x minus 4. That's the remaining factor. You could do this problem in so many different ways. But however which way you slice it, the answer is what I just circled right there. X minus 1, x plus 3, x minus 4. You could do it in any number of ways. How do you start it? You start it with synthetic. You look at the graph, you visually identify a 0, you divide that thing out, and then see if you have options. The options will come to you if the resulting equation is a quadratic. If it's quadratic, you have those options. If it's not a quadratic, you will have to continue with synthetic division, whittling this thing down until you get a quadratic. That's what you're going to have to do. It's what you did on that homework in the book. It's what you're going to do on this edge elastic assessment, if you haven't already done it, of course. That is due tomorrow by 2 o'clock. I need you to make sure you're getting that thing done. Now, at this point, I am going to wrap up everything that I've been doing today. I am going to sign off in a few minutes. I know that there's a little bit of a delay on what I'm saying and what's showing up in the live stream, so obviously that's why I'm kind of stalling it out a little bit, but that's okay. I will not see you again until Monday. On Monday, supposedly, I should be back in my classroom, but you will not, which I feel like it defeats the purpose. Like, you're gonna, hey guys, let's quarantine for 2 weeks. Hey teachers, come on back to the building. Yeah, that makes perfect sense. I really, really don't want to. I'd rather stay here. I have such a better setup here. But anyway, I digress. I'm going to wrap it up. Thank you guys for joining us today. If you have any specific questions, make sure you are emailing me so that we can talk about those things. Now that I have this fancy little setup right here with my own makeshift Elmo camera, I made this myself out of PVC piping, and I'm using my phone as an additional camera. It's fantastic. I can answer questions much more efficiently than other things. I don't know. Anyway, I'm going to sign off. You guys have a great day, and we'll see you later.